In the last class, we had started discussing the relationship between the discrete Fourier series and the discrete time Fourier transform, and this is how far we had gone. So we had said that if we have a periodic sequence and its discrete Fourier series is x tilde of k, and they are all periodic with period capital N. Then what we had realized from our discussion in the last class is that this x tilde k corresponds to equally spaced capital N samples of the DTFT of one period of x tilde n. So if you define x of n as that one period, and without loss of generality, we can take it to be the principal period between 0 and n minus 1. So n equal to 0, 1, up to n minus 1 and 0 otherwise. So if we take a sequence by taking just one period of our periodic sequence, and we associated with that sequence is the DTFT x of e to the j omega, then what we know is that x tilde of k is simply equal to samples of x of e to the j omega at omega equal to 2 pi k over n. Okay? So we divide between 0 and 2 pi, we divide it in n intervals. We sample it at n points. Okay? And the discrete Fourier series coefficients are simply given by those n, the discrete time Fourier transform at those endpoints. Okay? So if this is your, let's say, periodic sequence with period of, so you have the period of this thing is 10. Okay? It repeats itself after every 10 samples. Okay? So it's a periodic sequence, and what we can compute is the discrete time Fourier transform of this one period. Okay, so just look at between this 0 and 9. That's the discrete time Fourier transform. It takes the form sine over sine. Right? This is the amplitude, and if you go down, this is the phase. And what the discrete Fourier series coefficients, the way they are related to this DTFT is simply you take samples of that after every 2 pi over 10 radians. Okay, so this is your first discrete Fourier series coefficient. This will be x tilde of 0. Okay. This will be x tilde of 1, and so forth. So this is, you're computing the samples in the magnitude, and these are the, if you go down, you see the samples in the phases. Okay, so that's rather easy to see what is the relationship. If you are given a discrete Fourier series, how is it related to the discrete time Fourier transform? Next, what we are going to now discuss is if you are given a sequence, any sequence, and if you sample the discrete time Fourier transform of that sequence, how is that related to the discrete Fourier series? So now what we are going to do is that start with the DTFT and relate its samples to discrete Fourier series of some sequence, some periodic sequence. Okay. So the starting point is suppose we are given a sequence xn, and we are not going to now say anything about that xn. We are not going to say that that xn has a length of n or whatever. It could even be an infinite duration sequence, okay? Just some sequence xn, and that sequence has a Fourier transform, discrete time Fourier transform x of e to the j omega. Okay? And the question we want to ask is, let's sample the discrete time Fourier transform of this sequence at n points. Okay? What can we say about those samples? So this is effectively talking about sampling in the frequency domain as opposed to sort of sampling in the time domain. Right? Now we are doing a dual of what we have been doing before. So we want to sample we want to compute n samples of x of e to the j omega. So effectively, if you look at your z-plane, this is the unit circle, okay? And you are going to compute samples after every 2 pi over n radians. So like this is 2 pi over n. And let's put those samples, I'll still call them in a sequence x tilde k equal to x of e to the j omega for omega equal to 2 pi k over n. And it's clear that the reason I have put this tilde is because actually if you keep on sampling, since it's the unit circle and you have this periodicity, if you keep on sampling this after every 2 pi over n, once you traverse the whole unit circle, you will start repeating those same pattern. Right? So you have this periodic sequence. So if I compute my DTFT at n points and I put it in a sequence x tilde k, then effectively I get a periodic sequence of period capital N. Okay? That just follows from the periodicity of the unit circle. Now, since it's a periodic sequence, I could say that this sequence is related to some discrete Fourier series coefficients of a sequence. Okay, so this means that x tilde of k corresponds to the discrete Fourier series coefficients of some periodic sequence x tilde of n. Okay, and our goal is to find this x tilde of n. And based upon the previous discussion, actually, if your xn was smaller than, had a length smaller than capital N, then this x tilde of n will just be periodic repetition of that sequence. Okay? But if we are not making any assumption about the length of our sequence xn, the question is, if I sample the DTFT at n points of some sequence, what is this x tilde n that it corresponds to? Now, to compute x tilde n, we simply use the synthesis equation of the discrete Fourier series. So we apply the synthesis equation. X tilde of n is given by 1 over n summation k equal to 0 to n minus 1 x tilde of k wn minus kn. Okay. And now we input the value of x tilde k. So remember, x tilde of k are samples of our DTFT, and our DTFT is given by since we are not making an assumption about the length of the sequence, that is m minus infinity to infinity x of m e to the minus j omega m. And we are going to sample that at omega equal to 2 pi k over n. Okay. I have put m here instead of n because I don't want to use the same n that's being used here earlier. So that is simply m from minus infinity to infinity x of m e to the minus j 2 pi k n over m. So we simply plug this value in the above equation, the synthesis equation, to get x tilde of n equals 1 over n summation k from 0 to n minus 1, then summation m from minus infinity to infinity x of m w of n k m and w of n minus k n. Okay, after that I'm just going to do the changing the order of summation, take out the summation over m outside, pull xm outside, okay, and take this 1 over n inside, the other summation k equal to 0 to n minus 1, wn, and I just write minus k of n minus m. Okay. Now, what I'm going to do is define p tilde of n as 1 over n summation k equal to 0 to n minus 1 w of n minus kn. Okay. So if I compare this thing to this p tilde n, well, this is just p tilde n with a shift. Instead of n, I have n minus m. Okay, so this whole thing is actually p tilde of n minus m. So I just write that out. I have summation over m x of m p tilde of n minus m. So that's my sequence x tilde of n. Now let's try to simplify it further. What is this summation? This summation is nothing but convolution. So this means that this is equal to convolution of xn with p tilde of n. Okay. So let's call this equation star, and let's find out now. Let's simplify p tilde n further, which we had done something similar earlier, but I'll just repeat that. So p tilde of n is this 1 over n summation k from 0 to n minus 1 w of n minus kn. Okay. So the way to solve this is use the geometric sum, and if you do that, as long as n, little n, is some multiple of capital N, okay, as long as this little n is multiple of capital N, this will be what? This will be just 1. So you are adding n ones divided by n, you get 1. Okay. This will be true as long as n is some multiple of Rn for any integer n r. Right? And if that is not the case, then you use the geometric sum formula and you find out that it will be 0 otherwise. So this P tilde n is effectively just a periodic impulse train, which has one at n equal to 0, n equal to capital N, n equal to 2n, n equal to minus n, and 0 everywhere else. Okay? So this P tilde n is effectively just a periodic impulse train at every multiple of capital N. Okay? This is what P tilde n looks like. An impulse, 0, 0, 0, so forth, then another impulse, okay, at n, and similarly an impulse at minus n, and so forth. Okay. So let's write that down. We have x tilde of n equals x of n convolution with this periodic impulse train, delta of n minus Rn, and by the linearity of convolution, I just take xn inside, and then if I convolve a sequence with an impulse, all that happens is the sequence gets shifted to the location. So at the end, what we get is r from minus infinity to infinity, x of n minus Rn. Okay. So what do we learn from here? That if we sample the DTFT of any sequence xn, okay, then the samples correspond to the discrete Fourier series coefficients of a sequence x tilde of n, which is simply given by adding your xn after every n samples. X of n, you just periodically repeat x of n. You keep on adding those copies after every n samples, regardless of whether xn is of length n or not. Now, this looks very similar to what we discussed earlier. But the difference is, what does one period of x tilde n look like? So if xn was of duration less than n, or length less than n, less than or equal to n, so if xn had a length less than or equal to n, and you just take this xn and you keep on adding after every n interval, you shift it by multiple of n and you add, then any one period of x tilde n will just be xn. So any one period of x tilde n will be equal to xn in that case. And we can recover xn from x tilde n. Right? Just take the first period. So we can define x tilde of n as x of n as x tilde of n for n equal to 0, 1 up to n minus 1 and 0 otherwise. Okay. But this is only true if your xn was of duration less than or equal to capital N. If you take the samples of a sequence at n points, but the length of the sequence is bigger than n points, then you have the notion of effectively time aliasing, which is that the sequence gets added on top of each other in any one period of your periodic sequence does not correspond to xn. Okay, so we'll see it pictorially, but let's just, so if xn is not limited to n from 1 to n minus 1, then xn cannot be recovered from x tilde n. Okay, the phenomenon is very analogous and dual to the time sampling. Here what is happening is we are doing sampling of the DTFT of a sequence. We are doing sampling in the frequency domain. Okay, and those samples correspond to the discrete Fourier series coefficients of a periodic sequence. And if the signal happen to have a finite duration, so to avoid, for example, sampling, traditional sampling, to avoid aliasing, we need that the frequencies in our signal must be limited to some period, right? Now we are doing sampling in the frequency domain, and we are saying to avoid what we call time aliasing, to be able to recover your original sequence from the samples in the frequency domain, you must have your sequence limited to length n or smaller. Okay. So here is a sequence xn of length 9. Okay. And if you sample the DTFT of this sequence at 9 points, so or higher, then you can recover it from the periodic extension that you get of that signal. So in this example, this signal has length of 9. Okay, if you take n equals to, let's say, 12, so you take 12 samples of its DTFT. Okay, then those samples correspond to the discrete Fourier series coefficients of this periodic extension of the signal. You repeat this signal after every 12 or multiples of 12 samples. So this is your first copy from 0 to 11, then you repeat that. Okay, since the repetition interval is bigger than the length of your sequence, since n is bigger than or equal to 9, the original sequence lives in this periodic repetition. Effectively, there is no overlap of different copies in the time domain. There is no aliasing. Okay, you take samples of your DTFT, you can compute its inverse. You can use the synthesis equation to calculate x tilde n, and from x tilde n you can compute this xn. But let's take the example where you're the same sequence, but now I take only n equal to 7 samples. Okay. The discrete Fourier series coefficients correspond to 7 samples of the DTFT, which we are not showing in this picture, by the way. Okay. So the 7 samples correspond to, if you use the synthesis equation, they will correspond to this x tilde n. You take your xn and you repeat it after every multiple of 7 samples. So first time you get 0 to 9, but then you add another one before the sample gets done, and you have effectively aliasing. Different copies overlap with each other in time now. So this is, instead of doing frequency aliasing, what you are seeing is time aliasing. Okay, which means that if you compute 7 samples of the DTFT of your sequence, it's not enough to recover that sequence. Okay? So the point that this is trying to make is, first of all, to recover a sequence, you don't need the whole DTFT. Okay? DTFT is a function of little omega, which takes on infinite number of values from anywhere from 0 to 2 pi. But to know that sequence, you don't need the whole DTFT. All you need are a few samples of your DTFT. But how many samples you need? You need at least as many samples as the length of your sequence. If you don't do that, then you can't recover your original sequence. Very analogous to the sampling of a sequence in time domain. Now we are doing sampling in the frequency domain. And the fact that we can represent the whole sequence by just a few samples of its DTFT is the heart of the definition of discrete Fourier transform. Okay. So the main message of this discussion is that we do not need the entire DTFT of a sequence xn to recover the sequence. As long as the sequence has length less than or equal to capital N, and we take n uniformly spaced samples. Now that is the key. You can't just take n samples of your DTFT, for example, by putting them all in the first quadrant. They have to be uniformly spaced by 2 pi over n. Samples of the DTFT then we can recover our sequence and what will be the recovery procedure? We call our samples the discrete Fourier series coefficients of a signal. So we first do x tilde of k, which are our samples, x of e to the j omega, 2 pi k over n. From that, using the synthesis equation, we compute the periodic sequence whose discrete Fourier series coefficients are these x tilde k. Okay? So that will be simply 1 over n, k from 0 to n minus 1, x tilde of k, w of n minus kn. And then we just look at one period of that sequence. So take x of n equal to x tilde of n for n from 0, 1 up to n minus 1 and 0 otherwise. Okay. And the basic assumption is that xn has length less than or equal to capital N. Okay. Now this very relationship between the samples of the DTFT and the discrete Fourier series actually help us define formally the discrete Fourier transform. Okay. So since we know in this case that n samples of my DTFT are enough to recover the sequence if the length of the sequence is less than or equal to capital N, we can define the discrete Fourier transform as just the discrete Fourier series coefficients associated with those samples and the one period of the periodic sequence corresponding to the sequence, okay, for the inverse discrete Fourier transform. So the formal definition of discrete Fourier transform is then based upon the discrete Fourier series. And you can forget about that relationship in most cases, but you cannot completely ignore that because there are many properties of the discrete Fourier transform that can only be derived if we keep this relationship in mind, as we will see. Okay? So let's look at the formal definition of the discrete Fourier transform, which we had already given in terms of the orthogonal or orthonormal transform aspect, but there we had not related it formally to the DTFT. Okay? Now this definition is trying to relate it formally to the DTFT of our sequence. So in the formal definition, we will assume that we are given a sequence xn, and it is a finite duration sequence with length less than or equal to n. What that means is that for sure after xn is equal to 0 for all n that don't belong to 0, 1 up to n minus 1, it may or may not be 0 within this main interval. Okay. Now we define a periodic extension of this x till x of n. So we define a periodic extension of xn simply x tilde of n equals summation r from minus infinity to infinity x of n minus r n. But since we are assuming that the length of my sequence is smaller than this periodic repetition, I can simply write that down as x of n mod n. So this is a shorthand for x of n mod capital N. Okay? And in case anyone has forgotten the modulus operation, that is, so n mod n is defined as the positive remainder, so as the quantity r, which is positive, belongs to 0 to n minus 1, such that n equal to q times capital N plus r. Okay? For example, minus 1 mod n capital N is simply n minus 1. I want to put xn equal to 0 for all n not in this set. Okay? Okay, so with each xn, we associate a periodic repetition, which is defined as xn mod capital N. And with each periodic sequence, we have a discrete Fourier series associated with it. So if I define max tilde of n as x of n mod capital N, then there is a discrete Fourier series with it, which is simply x tilde of k. But that x tilde of k, by the discussion that we had, that is simply equal to samples of the DTFT of my original signal xn. So that is simply equal to x of e to the j omega at omega equal to 2 pi k over capital N. Okay. And that is effectively the, once we construct this, then the DFT x of k of xn is defined as simply one period of your discrete Fourier series coefficients. So your x of t is simply defined as x tilde of k for k from 0, 1 up to n minus 1 and 0 otherwise. Or in other words, the relationship between x tilde k and xk is that x tilde of k is simply periodic repetition of x of k. Okay, xk mod n. So the functional definition of the discrete Fourier transform is the following one. Now you can write it explicitly in terms of x of n by doing the computations. Okay. So DFT of xn formally is defined as one period of your discrete Fourier series coefficients of the periodic sequence obtained by repeating your original sequence. If I actually try to write it down though, that is simply equal to, so assuming that I'm for k equal to 0 to n minus 1, I write x of k. Right? What is the definition of the discrete Fourier series? That is simply n from 0 to n minus 1, x tilde of n, wn of kn. But for n between 0 and n minus 1, my x tilde of n is x of n. Okay? So that is simply equal to n from 0 to n minus 1, x of n, which is exactly the same definition as we saw earlier. So definition-wise, nothing is going to change here. But the reason we are going through the hoops for relating it to the discrete Fourier series is because we want to be able to derive some other properties that are not easily derivable by just looking at this equation. Okay? So if you, there are two ways that you can say discrete Fourier transform is defined. One is, of course, just this direct definition, right? This is the definition which is just a function of your original sequence. But the way this definition comes up is saying that actually your DFT coefficients correspond to the principal period of your DFS coefficients, one period of that. And the discrete Fourier series coefficients correspond to the periodic repetition of x tilde n. Okay. Similarly, if you ask what is the inverse DFT formula, that is simply just by the fact that if you look at one period of your x tilde n, right, that is equal to xn. So your inverse DFT is simply equal to the period x tilde of n for 0 between n between 0 and n minus 1, 0 otherwise. Okay. And once again, we can try to write down, so x tilde of n is, we had defined it as 1 over n, k from 0 to n minus 1, x tilde of k, wn of minus kn. Okay. But x tilde of k between 0 and n minus 1 is the same as x of k. So that is simply equal to 1 over n k from 0 to n minus 1 x of k. Okay. So we can define xn like this for the inverse DFT formula. This is our inverse DFT formula. Okay. But it is valid only for n equal to 0, 1 up to n minus 1. If you evaluate it for any other value, it's not going to give you 0. It's going to periodically repeat itself. So the main purpose of this discussion is the formulas for our DFT, whether we are talking about the analysis or the synthesis expressions, they haven't changed. But what we have argued is how do they relate to the discrete Fourier series, which is constructed by taking a sequence and periodically repeating it. Okay. And so that part will be used when we are trying to cover some properties of the discrete Fourier transform. So we can try to go through the discussion we had in that formal setting, even though we forget about this periodic extension and the discrete Fourier series when we are normally computing the discrete Fourier transform. So here is a sequence, its length, xn, its length is 5, okay? And we plan on computing its DFT, a 5-point DFT. So our n equals to 5, and that means that that sequence gives rise to a periodic sequence x tilde n, which looks like 1 all the way. Okay. Now the DTFT of that length 5 sequence looks like this sine over sine. It's periodic, right? And the discrete Fourier series coefficients correspond to samples of this, and the DFT coefficients just correspond to the same samples when we look at the principal period. Okay. So in general, when we are having the discussion about the discrete Fourier transform, we skip the equation B, this figure B and C altogether. We simply say that this sequence of length 5 has a discrete time Fourier transform like this, and so the DFT simply corresponds to samples of this DTFT. Okay. Now there is this middle way by which you can arrive at this, but as I said, we can ignore that for most cases. Now if I take the same sequence, it's the same sequence with length equal to 5. But now I want to compute the DFT, which is a 10-point DFT. Then that gives rise to this periodic extension x tilde n. Okay. So you now repeat this. And now your coefficients correspond to the same DTFT sampled at now every 2 pi over 10 radians instead of 2 pi over 5 radians from before. Okay. So now these are samples of x of e to the j omega at omega equal to 2 pi k over 10. Okay. And in most cases, you can simply just get rid of this figure. When we are trying to evaluate a sequence using DFT, we can simply ignore the fact that we defined it using the discrete Fourier series. But it is important that we keep that perspective in mind, because in some analysis, when you're trying to do that analysis, if you ignore that completely, then you can get in trouble. So that's the basic purpose of why we want to define it formally through the discrete Fourier series. Otherwise, there is nothing fancy about, if you understand it from that perspective, the definition or the operational meaning that you know from your undergraduate days is not going to change. Okay, let's talk about the properties of the DFT. The first property, which is any linear transform, you have been doing that for a long time in pretty much every transform you must have studied, which is linearity. Here we have to just be careful about the number of samples that we are computing of our DTFT. So if x1n has a DFT x1k and x2n has a DFT x2k, then you have to first of all take n, the length of your DFT, as greater than or equal to the length of both the sequences. Okay, n1, n2, where n1 and n2 are, where ni is just length of xi. So first of all of these DFTs have to be computed using the same endpoint, and the number of points of the DFT has to be bigger than or equal to the max length of any one sequence. Okay, if that is the case, then if you add those two sequences, then the DFT of that is simply equivalent to adding the respective DFT coefficients. Pretty trivial to verify that, so we won't spend time on that. A different property which we don't see in the case of other transforms is that of circular shift. And this property is best understood by going back to the definition of DFT in terms of the discrete Fourier series. So let's first relate it. What is circular shift property about? So if we are given a sequence xn and it has a DTFT x of e to the j omega, okay, and then we multiply this DTFT with some phase shift. So we do e to the minus j omega m x of e to the j omega. So phase shift in the discrete time Fourier transform has a meaning in time domain, and that meaning is linear shift. So if we have a phase shift in time domain, that is simply equal to linear shift in the if you have a phase shift in the frequency domain, that is simply equal to a linear shift in the time domain in DTFT. Now let's ask a similar kind then of a question in the case of the discrete time Fourier transform. Okay. So let's assume that we have this xn and it has a DFT x of k. Okay. And the only thing we are saying is that the DFT is computed with n which is greater than or equal to length of x of n. In particular, n could be exactly equal to the length of x of n, and now I change my coefficients by multiplying them with some sort of a phase shift of this nature, e to the j 2 pi k over n times m x of k. Okay, let's call these coefficients x1k. The question is, if I multiply my DFT coefficients with this phase shift, okay, e to the minus j 2 pi k over n times m, what does that mean in terms of the sequence? What is this these DFT coefficients correspond to which time domain sequence. Now that time domain sequence couldn't be just linear shift because I'm allowing that my n could be equal to the length of the sequence. So if it was a linear shift, for example, then I would have a bigger sequence than the length of the sequence. So it definitely can't be coming by linear shift. What does it come about? We are interested in finding out what is this x1n given by as a function of x of n. Okay. And the way we derive that is by going back to the definition of DFT based on the discrete Fourier series. So what does it mean that we have xn and DFT xk? What it really means is that we have a periodic extension of xn. So this definition actually comes from the discrete Fourier series definition, which is that we have x tilde of n, which is simply given by this mod operation of n, and that x tilde of n has a discrete Fourier series which is simply given by x tilde of k equal to periodic extension of the discrete Fourier transform coefficients. Okay, this is really the definition of DFT. And to understand this relationship, we have to actually keep on working in the discrete Fourier series domain, and finally we will translate that into the DFT version. Okay? So let's now define x1 tilde of k. Okay? So we are interested in finding out what does this x1k, these DFT coefficients correspond to what x1n. So for that, we will define the corresponding discrete Fourier series coefficients. Okay, so we define x1 tilde of k equals x1 of k, periodic extension of our coefficients that we are interested in. Okay, and then we plug in that value. So it's e to the minus j 2 pi k mod n over n times m and x of k mod n. Okay. Now, because of the periodicity of this term, right, whether I have k mod n or just k, it doesn't change the answer. Right? So that is simply equal to e to the minus j 2 pi k over n times m. Okay, times x of k mod n. So what this means is that x1 tilde of k is simply equal to e to the minus j 2 pi k over n times m, x of k n, which is equal to e to the minus j 2 pi k over n m x tilde of k. Okay. So we have a new discrete Fourier series coefficients, a new set of discrete Fourier series coefficients which are given by simply a phase shift of my previous discrete Fourier series coefficients. Now, in the last class, or perhaps the one before that, what we saw was that if you have a phase shift in discrete Fourier series coefficients, they correspond to a linear shift in the periodic sequence for which you computed the discrete Fourier series coefficients. So x1 tilde of n are actually discrete Fourier series coefficients of something which is x1 tilde of n, which is simply x tilde of n minus m. So that's the discrete Fourier series property that we had done earlier. Now x tilde of n is defined as xn mod n. So I just input that value. So I get x of n minus m mod m. Okay. And now I have derived this expression. I have that x1 tilde of n is equal to x n minus m mod n. This is a discrete Fourier series of x1 tilde of k, which is x1 of k mod n. Okay. This means that if I do the translation of from discrete Fourier series to the discrete Fourier transform, okay, the discrete Fourier transform, that means corresponds to one period of that, which is what we had started with, e to the minus j 2 pi k over n times m x of k, right, which is just this thing, periodic repetition without the periodic repetition. And x1n is simply then, x1n is simply the principal period of this thing. So x1n is simply x of n minus m mod n for n equal to 0, 1 up to n minus 1 and 0 otherwise. Okay. So what that means is that if you multiply your DFT coefficients with e to the minus j 2 pi k over n times m, that gives rise to your sequence gets changed by this operation. And what is this operation called? This is called circular shift. Okay. The best way to understand circular shift is you can either look at the periodic extension of your original sequence and then linearly shift it and focus on the main period. Or you can think of the circular shift as simply that you are trying to rotate. You have these sequences sitting on a dial and you are just rotating that dial by the amount that you have to circular shift. Okay? So we will now take a look at an example of this circle. So this is our original sequence xn, okay, of length n, and this is its periodic repetition x tilde n. So there are two ways of computing the circular shift. Let's say you want to do a left circular shift by 2. Okay. You either take this periodic thing and you move it to the left by 2. So move it to left by m equals 2, and you get this new sequence. And then the circular shift just corresponds to the sequence that is between this principal period. Okay. Now the other way of thinking about this is that you actually take just your primary sequence. You simply take your primary sequence and you move it to the left, but every time a sequence goes out of this range, you rotate it back and you put it back here. Okay, so if you shift it by 2, you go and put this here and you go and put this the other in the next position, right? So you go and put this here and this value gets put here, this value gets put here. And you can keep on doing this as many times as you are asked to circularly shift. Okay, this is the way to originally see the circular shift. This through this x tilde n by shifting this. But once you get enough experience, then you can simply compute the circular shift either by left or by right. Okay? If you are trying to do circular shift to the right, it will be a similar operation. So your output is, if you go by the traditional definition of discrete Fourier series, you shift it, and then your output is simply the principal period, which is this thing. But once you get really good at it, you don't really have to do these intermediate steps. So once you get comfortable with this, of course, the usual way to think about the circular shift, whether you are doing left circular shift or right circular shift, is you can use this expression where you basically have these values. You start with the original sequence, okay? And so these blocks or these squares correspond to the values of your sequence, and outside that you have the indices. So you have index 0, index 1, index n-1, and index n. Okay? And based upon the shift, you rotate this inside thing. So if the value here was, let's say, 2, and the value here was 3, right? You rotate this thing based upon the circular shift you are doing, so that the end sequence you get has the same length as the sequence you started with. Okay? But where the values end up depend upon, so if you do shift by 1, then this 2 will now start appearing at 1, and the value at the last entry will start appearing at 0. This is when you are right shifting by 1. Okay? If you are left shifting, then you will rotate it the other way. And so it's a simple exercise that you can try to get comfortable with. But in reality, the definition is you can either the definition of circular shift comes from understanding about the discrete Fourier series relationship of the DFT. Let's look at another property, which is that of the duality property, which again is somewhat difficult to derive if you don't think about the relationship of the DFT with the corresponding discrete Fourier series. So you are given Xn, and it has a discrete Fourier transform x of k. And what we are trying to ask is there a duality property, which means that if I somehow take the sequence that I had in the DFT domain, and I make that a time domain sequence, and I compute its DFT, is that somehow related to x of n? Okay? But to approach that, we really have to go back to the duality property of the discrete Fourier series. So this Xn, of course, has a corresponding discrete Fourier series interpretation, which is n mod n has this discrete Fourier series x tilde of k given by repetition of your DFT coefficients. Now, DFS has a duality property which says that if I define my x tilde 1 n as simply my discrete Fourier series coefficient, so this is capital X, okay? So I take the same coefficients, but now I treat them as a time domain sequence, okay? And then the relationship is that has a discrete Fourier series which is given by n times x tilde of minus k. Okay. Now, in that case, we can derive the relationship between a duality property based upon this discrete Fourier series and a duality property based upon the discrete Fourier transform. So I can define my x1k, okay, as equal to n times x tilde of minus k for 0 between k between 0 and n minus 1 and 0 otherwise. Okay, so I simply take these discrete Fourier series coefficients and I write them as my DFT coefficients. And now I plug in the x tilde minus k value. So x tilde minus k is simply x of minus k mod n. 0 is less than k is less than otherwise. Okay. So based upon this relationship, I can use this to say I have, if I define a sequence which is xn using, now we are going to the DFT domain, it has a DFT which is given by this x1k. Okay, it is given by n times x of minus k mod n. And the assumption is we are talking about between 0 and n minus 1. Okay. So the upshot is that if you are given a DFT pair xn and x of k, then by duality property, if you treat that x of k as a time domain sequence, then your new DFT coefficients are nx minus k mod n. Now minus k mod n is simply equal to n minus k. So we are dealing with k between 0 and n minus 1. So that is equal to n minus k for k from 1, 2 up to n minus 1, and 0 for k equal to 0. Okay. So what this means is that you effectively have, you again have this circular shift going on, but this way the circular shift is explaining that is very easy. Basically, your new sequence is simply at 0, it just gets the value 0 with the, of course, the scaling capital N. Okay, but then it just gets moved, everything that was at, something that was at 1, it gets moved to n minus 1. Something that was at 2, it gets moved to n minus 2, and so forth. If you look at this example of our xn is just a rectangular pulse, okay, and these are its DFT, these are its discrete time Fourier transform, and the DFT coefficients just correspond to the samples of this DTFT. Now, if I decide to, instead of these DFT coefficients, I actually treat them as my time domain signal. Okay. So now I'm calling the real value, I'm defining a new time domain signal where the real value actually is the same as the DFT coefficients of the original sequence. Okay. So they are exactly the same, but now I'm treating this as the time domain signal. And similarly, I'm the imaginary part, I'm treating the coefficients, the imaginary part of the coefficients as the imaginary part of the time domain signal. Then, since I know what my original time domain signal was, the DFT of this new time domain signal is simply related to this time domain signal, where this 0 stays as 0, but this 1 moves to n minus 1, this 2 moves to n minus 2, and so forth. And so you don't have to compute it. So in this case, they are using a 10 point. So at 0 you had 1, it gets 10. And then you get here n minus 1, you get the value 1, okay, multiplied by 10 and so forth. So this is your new sequence without computing the original one, okay. It's very different from the duality in DTFT where the shape doesn't change. Based upon your n, your sequence has completely changed. Previously you had a sequence, your previous shape was just a rectangular pulse. So in DTFT, for example, we say you take the transform of a rectangular pulse, you get a sinc. You take transform of a sinc, you get a rectangular pulse. In this case, you take the transform, DFT transform of a rectangular pulse, you get these coefficients. But if you take the transform of these coefficients, you actually get this circular shifted version of your pulse. Okay. And if, of course, your n was bigger, this gap would keep on getting bigger and bigger. So again, that is another property of the DFT that cannot be simply derived by looking at the DFT equation. You have to go back to the relationship with the discrete Fourier series and be able to interpret that. So with this, we'll conclude today's lecture. We'll come back to some of the other properties. We'll spend less time on them except the property of circular convolution. And we'll try to wrap up Chapter 8 pretty soon.